Okay. So thank you very much for the invitation to come here. And I'm really happy because it's a beautiful place. I think it's very stimulating. Just walking around, I feel like, the people like to work and work hard here, and it's beautiful, really. I was here a long time ago. It was different. I think it was renovated in many parts, and I think it's identical. I don't know. So, okay. Doesn't matter. Sorry about that. Okay. Okay, good. So, basically, what was said by Maria, I confirm. I'm an experimentalist, unfortunately, and I work with heavy ion collisions. Not only heavy ion collisions, but I think this is the main subject of research that we do. And so, in this talk, I will show you that this is a tool that you can use to study the equation of state under laboratory controlled conditions. Okay, so probably in most of the presentations that have been given today, you have been listening about astrophysical observations where you cannot put your hands. You have to wait for supernova. For example, the last one was 1987, and it was mentioned today. So it's very difficult to think that one can produce a supernova, or we know when or where to look for a supernova. It's very difficult. And for neutron stars, we are lucky. There are many more neutron stars, many missions in space where people try to measure size, radius, mass, of different things. But in the laboratory, we can control the conditions of temperature and density that we can produce thanks to the accelerators that we have in our laboratories, okay? So I will introduce a little bit the concept of the equation of state as seen with the eyes of an experimentalist. So sorry if you will find something very trivial or a little bit stupid, but that's that's a fact. And then I will say a few things about phase transitions because it's important for symmetry energy, and then of course symmetry energy. And I will show you that heavy ion collisions are actually a very multi-purpose laboratory where you can study bulk properties like the equation of state, nuclear matter, but also what I call femtoscopic properties that are more related to the size of femtometers. So properties, actually we can measure those sizes thanks to particle-particle correlations. Okay, so it's like the other side of the coin. So you have in astrophysics things that sizes of a few kilometers, like neutron stars. So it's like, we know microscopy, that's kind of kiloscopy, okay, kilometers. And in nuclear physics, we talk about femtoscopy instead of microscopy because we can actually probe sizes of the order of a few Fermis. And then I will conclude with some status of the art and where we are going in the future in this direction. Okay, so as I was saying, this is what we usually say, when we work with experimentalists. We consider nuclear matter an idealized system because we work with collisions of finite nuclei. So it's made of infinite number of nucleons. So you all know these things. So there's an isoscalar density, which is the sum of proton and neutron densities, an isovector density, which is the difference between them. And then, of course, the saturation density is a parameter that we need to know. It's important. It's basically the density, the average density in nuclei in the ground state. And we call physics at subsaturation whatever happens at below saturation density, and suprasaturation whatever happens above saturation density. And that's important from the point of view of laboratories because we access this region when we study heavy ion collisions at beam energy less than usually, while we try to access the above. Actually, when we say access, it's not really correct. What I mean is that the observables that we measure are dominated by this region where we are at low energies, and they are dominated by this region where we are at higher energies, because in the later stages of heavy ion collisions, even at higher energies, so you will go to low densities. However, we have probes, experimental probes, that are really sensitive to the high density region, okay? So, so we do collisions between massive nuclei, say, above a mass number 40, above that, so tin on tin, gold on gold. And we change the N over Z asymmetry to try to see what happens in terms of the effects of the symmetry energy on the equation of state. So about isospin asymmetry, you all know this. We have this parameter delta, which is the difference between the isovector and the isoscalar density. When delta is equal to 0, you have symmetric nuclear matter that has been studied for many years experimentally in heavy ion collisions. Then pure neutron matter is when delta is equal to 1, and you have been listening a lot about neutron stars today. When you have delta less than 1, you have asymmetric nuclear matter, and then that's the condition that we have usually in the laboratory when we do experiments, except when you study collisions between symmetric nuclei, that means delta equals 0. Of course, we never have this situation, so our results are always something that should be extrapolated when we go towards neutron matter that is extremely rich in neutrons. So as it was mentioned today several times, the equation of state is a relation between the energy, the density, the isoscalar density, the temperature, and also the isovector density, let's say. I mean, this isospin asymmetry here. So I would like to show these figures that were published in this nice paper, which is about heavy ion collision. I think it's one of the nicest and most complete papers on how to use heavy ion collisions to transitions and the equation of state. It was published in 2008, and they basically were mentioning how if we use a nuclear-nuclear interaction that looks like the van der Waals forces that we know for ordinary matter, you can deduce equation of states like isotherms or isobars for nuclear matter. And values are, this is the pressure divided by the critical pressure, and volume, and the density divided by the critical density. This is the temperature divided by the critical temperature. These are the isotherms, and we recognize that even for nuclear matter, you can expect something similar to what you would observe with ordinary matter. You know that there is a critical temperature, and below the critical temperature, there are regions where when you decrease the volume, the pressure decreases, which is very strange. So usually we would expect that if you shrink the system, the pressure should increase. These regions where the derivative of the pressure with respect to volume is positive are instability regions where matter doesn't like to be in one phase and starts to break up, and you have the coexistence between two different phases. And we observed that even experimentally in heavy ion collisions. So the important thing is that studying the equation of state with heavy ion collisions is a way to study nuclear forces, of course, because the equation of state depends on the interaction. So it's not only doing nuclear structure experiments with like direct reactions where you have transfer of knockout or all these things to study nuclear, the properties of the nuclear interaction, but we can also use these bulk studies with heavy ion collisions to infer something about the interaction between nucleons, which is an important topic for nuclear physics and for astrophysics, as you know. And when we do that in heavy ion collisions, there is an interlink that it's very difficult to break. So nuclear structure and nuclear dynamics play a game together, and it's very difficult to disentangle one from the other. You cannot access nuclear dynamics neglecting the presence of nuclear structure effects. And on the other hand, as I will show you later, you can do nuclear structure studies in heavy ion collisions, but you have to consider the specific dynamics and know it very well with your experimental setups. As I was mentioning before, these regions of mechanical instability usually are called the spinodal instability regions. The compressibility is negative, and you have the liquid-gas phase coexistence, even for nuclear matter. This is true, and the critical temperature is about 15 MeV. So this division between liquid and gas has been studied for many years, It occurs at temperatures of a few MeV up to 10 MeV. There are measurements about this, indications that something called coexistence between a liquid and a gas phase exists. And from a phenomenologic point of view, usually we call a gas-like phase when you break the system into individual nucleons or light clusters. So you imagine you have a collision at high energy, you destroy completely the system, you associate this to a sort of phenomenology of the gas phase. While on the other hand, when you have heavy nuclei, you have studied for sure the liquid drop model. It's a liquid because indeed nuclei behave like liquids. When you have complex fragments or residues of fusion or fission residues, you can say that those are the phenomenology of the liquid phase. And in between, you can have situations where the system breaks up into many fragments of different sizes. And this is sort of considered a phenomenology that can be associated to the coexistence between a liquid and a gas phase. And this is what happens in these instability regions of the equation of state, okay? So all this has been the topic that has been addressed theoretically and experimentally for many years. And more recently, let's say with, yes, please, yeah. Oh, it's not, of course, it's not. Yeah, yeah, sure. Hmm? Say it again. Mhm. Yeah, it's, no, I agree. I mean, it's not so easy. So experimentally, we don't measure pressure. We can measure temperatures. We know how to measure temperatures. We know how to measure densities. I will try to show something this during my talk. But pressure, we don't know. So what we do is that we use models, theoretical models that have the equation of state as an input. I will say something about transport models, as they are called. You put inputs from, hypotheses that are related to quantum nuclear many-body systems. And then these models will follow the collision between nuclei, produce fragments, and then you compare the calculated observables to the observables that we measure experimentally and try to see if you can reproduce it. And then you say, okay, my input about the equation of state and was correct. So that's the only thing that we can do. We cannot access directly, except some observable. Something can be measured, like temperatures or densities, but not more than that. Yeah. Yes, this is infinite nuclear matter. It's not finite. Oh, sorry, yes. Sorry, Aura. Yeah. Yeah, okay. So until now, we are talking about infinite nuclear matter. I didn't get into what I'm saying is that experimentally, if we want to see a liquid phase, we do not have infinite nuclear matter. So we call phenomenologically liquid the fragments and gas the isolated nucleons. So I will show you how this happens in collisions. And within the equation of state, this has been shown for sure. I'm quite sure that this was discussed. If we talk about the energy as a function of the isoscalar density and this delta asymmetry, isospin asymmetry in nuclear matter, usually it is decomposed as a term that is the symmetric part that doesn't depend on the asymmetry between neutrons and protons. And this has been studied experimentally in heavy ion collisions for many years. While there's another higher order term that is proportional to the square of this delta asymmetry. And the coefficient depends on this isoscalar density, and it's called the symmetry energy. This is the asymmetry term. What you can see here is that it depends on delta square. So the effects of this part over this part become more important when I consider more and more asymmetric nuclear matter. So this has been the investigation for many years, theoretically and experimentally. This is a plot of different calculations with Sker, Martre, Fock calculations. There are very different predictions, and we are trying to understand whether this density dependence is stiff or is soft. And there are regions at low density that are accessed at intermediate energies at laboratories like Ganil or the LNS in Catania. While if you want to go to the higher densities, you have to switch to other facilities like FRIB in the US, FAIR at GSI in Germany, and RIKEN in Japan. And of course, other facilities that are under construction, even in China or in Korea, South Korea. So just to give you a perspective of where we do experiments if we want to access different regions of this symmetry energy. What is important is that if we do experiments by increasing the N over Z asymmetry of the interacting nuclei, we hope that we obtain results that amplify the effects induced by this term in the equation of state. We hope. Okay, we try to do as much as possible with studying our experimental data to extract sensitivity to this term here. So the important thing is that we want to explore systems where we have density gradients, temperature gradients, and N over Z gradients. We want to produce them, or eventually they exist, like in neutron stars, and can be studied. So there were already many discussions about astrophysical observations, like supernova, neutron stars, or gravitational waves, which is part of the phenomena associated to the existence of neutron stars. And then, of course, what I will talk today is about the dynamics of heavy ion collisions. So this is a typical cartoon that you can deduce when you do collisions with some models. As I said before, you put some input about the interaction, the equation of state, and then you let the system evolve. If you have a phase of pre-equilibrium emission and of compression of nuclear matter, then when there is this compression at some point, the nuclear-nuclear interactions starts to go in the region where you have the repulsive core of this force, and you have a reaction to that manifesting with an expansion and flow of nuclear matter that goes rapidly at low densities. When it goes at low densities, it enters in this instability region where there are mechanical instabilities, and you start to see the splitting of fragments and the splitting of nuclear matter into fragments and light particles. This thing here is a laboratory where you can study bulk properties like the equation of state, phase transitions, and symmetry energy, or femtoscopic properties by looking at correlations between all these fragments that you produce. For example, you can have decays of resonances that are produced here. You can produce fragments that are excited. Some of them might be exotic nuclei, and you detect the final products of these decays and reconstruct it with invariant mass reconstruction and study the nuclear structure properties of these fragments that are produced. So you can do resonance decays to study sort of medium nuclear structure in the sense that you are connecting dynamics and structure together to get information about the properties of these fragments in this dilute and hot nuclear medium. Okay, so concerning bulk properties, so we go into the nuclear equation of state part, and you can see here, these are simulations with a quantum molecular dynamics model. It's one of these transport models that are used where you put some interaction in there, so some equation of state, and you let the system evolve. And this is the profile of the density of the center of this collision as a function of time. You start with the saturation density. Okay, this is rho over rho zero. You have compression in the initial phase of the reaction, and then the system expands and goes to the low density region. And also, if you try to look at the temperature, you would see that the system will have a phase of heating, and then it starts to cool down and saturates around 5 MeV, according to this model, okay? What you can see is here also is that if you change the beam energy, okay, the velocity at which you have the collision between these nuclei, you can change the maximum density that you can reach, and you can also change the temperature that you can put into the system. So somehow we can say that we can control, I mean, not so easily, but in some sense we expect that the beam energy and also the combination of the mass of this nuclei can be used to have some hands on the temperature and the density that can be achieved by these systems, okay? And of course, you can also control somehow the isospin asymmetry if you simply choose collisions between nuclei that are very neutron rich or very proton rich. So this is another thing that you can do before you start your experiment. So somehow you put some pressure and so put some heating and put some isospin, more or less isospin, depending on what you decide to study in your experiment. And then other type of properties are the femtoscopic properties. I was mentioning before, you can have a lot of resonances that decay. This is what we can do. In a sense, another way of looking at this problem is that this is you have this the stability line, and also you have all the nuclei that we know and what people think that can be accelerated at different laboratories. So what we do usually in laboratories is to study the dynamics and structure under extreme conditions. And we can go, of course, towards the heavy element line. So we extreme conditions of mass and charge, which is the super heavy element domain. Or you can just go around, away from stability line. So you are starting to study the extreme conditions of isospin. And for example, you have phenomena like the neutron halos that are very beautiful. And but with heavy ion collision, somehow we can say that we are going beyond saturation, and we are starting to see how structure evolves when we go away from these conditions. So we can have, as I was saying before, supersaturation conditions and subsaturation conditions. And this is also another simulation done with another transport model called Blob. And you can see how things happen, how these fragments are produced. And here are there are a lot of structural properties that you can explore when you are away from these saturation density conditions. And this is what you can, for example, in one single reaction, one single collision, you can look at the correlation between several particles that are detected in the final state. And when you look at all these correlations, so you can reconstruct by invariant mass the resonances in their parent nuclei before decay. And you can see all these peaks that correspond to the internal structure of all these nuclei. Some of them are stable nuclei, others might be some exotic nuclei. For example, lithium-5 is not a stable nuclei. And if you study the details in the line shape of these correlations, you can reconstruct the structure properties of these nuclei. So somehow in heavy ion collisions, you have a lot of rich information. Of course, the drawback of that is that all of this is mixed with the dynamical effects, and so not so easy to disentangle. Okay, so but this problem is very important. If you have clusters, all these particles that correlate with one another, you affect dynamics. And this is shown here. For example, we measure experimentally the charge, the distribution of charge that can be produced during these collisions, okay? Event by event, you count how many z=1, z=2, z=3, up to z=30 you have, and you measure these blue points here. And then you try to use your model to reproduce this experimental distribution. And what you see is that if you do not include these cluster formation effects and correlations between these clusters, you cannot reproduce the data. Once you start to include this correlation in your model, you start to improve the reproduction of these general bulk properties of how the system breaks into fragments. So this is just to mention that there is an interlink between these two things, and considering in models the presence of these correlations between light particles is very important. So concerning the bulk properties, we said already something about the symmetry energy. In the last 20 years, people want to really understand what is the density dependence of the symmetry energy, okay? So we do experiments, and today I will focus on the low density region of this plot here, because there have been many more investigations, and also in our collaborations, we work a lot on this. This is the type of mechanisms that we use depending on the impact parameter. So in central collision, so you have, as we said before, compression, emission of pre-equilibrium particles, flow, and multifragmentation. In mid-peripheral collisions, you have the formation of this neck region between the projectile and the target. This is a low density region where you have the formation of neck fragments. And these neck fragments are sensitive to the symmetry energy, as well as multifragmentation here is also sensitive to the symmetry energy. While in more peripheral collisions, you do not have anymore the formation of a significant neck, But you have other phenomena that we call isospin diffusion and drift between projectile and target, and also the isotopic composition of these two guys at the end is sensitive to the symmetry energy. I will show you how this works in experimental data. No, no, no. This has to be experimentally. You can take all the events and classify them into different impact parameters. There are observables that tell us if a collision is central or peripheral. For example, in a central collision, for example, you expect to have a lot of particles produced, high multiplicity, so it's a more violent collision. If you are in a peripheral collision, in the event, you see only two big fragments that are produced. So you say this is another class of event. So here we do not have control, but we have control on the data afterwards. So we have billions of events. Yeah. Sure. It's not, so I would say that you can, it depends on how many observables you have to constrain the impact parameter. So for example, multiplicity, another observable could be how much matter goes in the transverse direction, because if you have a collision, you expect in central collision, you have more transverse emission rather than longitudinal, or you can have the shape of the event in momentum space that could be more compact or more elongated. All these things together, possibly with Bayesian analysis and statistical analysis, will constrain the impact parameter to the level of a couple of Fermis or something like that. For sure, yeah. Yeah. Right. Yeah. Right. Yes. Yeah. And at these energies also, because these are high energies, I mean, they're not very high, but they are high enough that you can use a kind of geometric approach where the cross section would be square of the impact parameter. So you will see that there are events where you observe almost the projectile and the target. These are the most peripheral events, and we know that this would correspond to the sum, roughly, of the radii of the projectile nucleus and the target nucleus. This is the largest impact parameter. While in certain events, you break up the system completely into light particles. That's, even when you have a frontal collision between two cars, of course, the most violent will produce the largest number of fragments. So there are some reasonable things, but they are connected to physics. If you have many observables, so you constrain even more the impact parameter gate, okay? So it's like dividing into windows. Certainly, these three conditions are clearly visible and can be identified very well. There is no doubt you can easily distinguish the presence of neck fragments from the absence of neck fragments. Okay, so I don't need to say that. So if we focus on this part, so the system breaks up into many fragments, and one of the first experiments that was done in this direction was done at MSU, studying central collisions between team 112 on team 112 and team 124 on team 124. You can see you change the N over Z, hoping to have some sort of effects of this isospin asymmetry on the dynamics. You keep conditions the same in terms of beam energy, and you try to see if your data, your results depend on the N over Z of the system and draw conclusions about the symmetry energy. This is a typical setup that was used. That was very advanced, very good isotopic resolution. You see in collision events that you can identify a lot of isotopes for many different elements. And this is the basis for doing this type of physics, of course. And for example, you can measure the isotopic distribution. So for each Z value, for each element, you can measure how many isotopes you detect for each reactions. So these are different isospin. For example, if you look at the squares here, this is the team 112 on team 112, and you see that you produce more proton-rich isotopes, while if you look at more neutron-rich collision systems, so you produce more more neutron-rich fragments. So you look at all these isotopic distributions and you divide them in order to amplify the effects of the event better. You make a division between the isotopic distribution in the neutron-rich and the isotopic distribution in the, let's say, the neutron-poor system. And when you do that, you observe experimentally that, so forget about the lower part of this plot. This is the same thing. For each element here, as a function of the neutron number, we have the ratio between the isotopic distribution in the neutron-rich reaction divided by the isotopic distribution in the neutron-poor reaction. And you see all these lines that are parallel and the same distance from one another. So that means that was observed 20 years ago, and it was compacted in one line, saying that there is a scaling properties, indicating that some degrees of equilibrium has been reached in the system. And the whole distribution can be described simply, these ratios between isotopic distributions can be described simply by knowing two parameters that are this alpha slope, that is the slope of this distribution. And if we look at the isotonic distribution, so we fix n and we look at the z distribution for each n value, you obtain the same thing, and these slopes are dominated by this beta parameter. So this scaling properties has been studied for a while, and it has been related directly to the effects of the symmetry energy in the coexistence between the liquid and the gas phase of nuclear matter. And I cannot go into the details, but what was observed is that when we increased the n over z of the colliding system, if there was no phase coexistence, if there was no effect of the symmetry energy, we would expect the n over z to distribute between the liquid and the gas phase in a uniform way. So you would observe that the total system in central collisions would follow these lines here. But what we observe experimentally, what we can extract is that the density of the free neutron gas is much larger than the density of the initial system. So it's like we are observing an enrichment of the gas phase with respect to the liquid phase due to the fact that we have reached this phase coexistence. And this has been known as isospin fractionation as an effect of the symmetry energy on the liquid gas phase transitions. And people working on transport models have been trying to connect this phenomenon to the density dependence of the symmetry energy. This is a model that has been developed many years ago, and Maria is one of the authors actually of this model. It's stochastic mean field calculations, where you can change the density dependence of the symmetry energy, and you follow the collision between two nuclei, for example, Tim-112 on Tim-112, a central collision. You see how fragments are formed, and in these calculations, they used to call liquid these big fragments and gas the isolated nucleons, and then see what happens when you compare what happens with different n over z of the collision system. And the interesting thing that could be observed at that time was that this neutron enrichment of the gas phase with respect to the liquid phase is sensitive to the density dependence of the symmetry energy, because you would expect something like that in case of an soft density dependence of the symmetry energy. But if you use a different type of this density dependence, you see that this asymmetry between the neutron enrichment in the gas and in the liquid is different. So in some sense, if we are capable of measuring this neutron enrichment, we could say something about the density dependence of the symmetry energy. So that's why this is how you connect properties of, let's say, infinite nuclear matter, like the equation of state and symmetry energy, to what you observe experimentally, typically in one of those experiments. So this was isospin fractionation that was studied for many years. And as I was saying before, it is sensitive to the density dependence of the symmetry energy. And as I was mentioning at the beginning of my talk, we are at low energies, let's say below 100 MeV per nucleon. So we are mostly exploring the region at low density in the equation of state and the symmetry energy. Now I want to show you another phenomenon that is studied very extensively in heavy ion collisions. This is what happens not in central collisions, but in more peripheral events. And that's what has been called isospin drift and diffusion. So now you have a collision not at zero impact parameter. And this is again a simulation with the same model, with the SMF model. A non-zero impact parameter, you have the formation of this region that it's like a neck connecting the two nuclei. And this neck is characterized by low densities as compared to the regions that are remainders of the projectile, of the initial projectile and the initial target. So there is a density gradient. You remember at the beginning of my talk, I said that it's important to produce density gradients. So what happens is that there is a drift of neutrons towards the low density region, and this has been called the isospin drift. Okay, this is one phenomenon that happens. And this happens even if you have two nuclei that have the same n over z. So it depends just on the density gradient inside the system, just because we are producing a low density region that wants to be more neutron rich. As I said before, the gas region wants to be the more neutron rich. The other effect is when you change the n over z. So now you make a collision, for example, team 124 on team 112. So they have different numbers of neutrons and protons. During the collision, together with isospin drift, you have another phenomenon, which is the diffusion of neutrons and protons between these two nuclei. And during the collision, they would like to reestablish a kind of uniform distribution of neutrons and protons all over the system. But of course, the system will break up before this process occurs. So at the end, you would have basically the systems that are, if you have a very long interaction time, then you succeed, of course, to have this uniform distribution. But if the interaction time is not long enough, which depend on the impact parameter and the beam energy, you break up the system and you have a different n over z of these two guys here, which is not the same that you had at the beginning. So the degree of change in this n over z is called isospin diffusion. And both phenomena, isospin drift and isospin diffusion, depend on the symmetry energy. And this has been expressed in several papers. So the flow of neutrons and protons here due to the isospin drift and isospin diffusion depends on the symmetry energy in different ways. The isospin drift is more related to the density dependence of the symmetry energy, while the isospin diffusion is more to the strength of the symmetry energy around saturation. And of course, if you study this phenomenon experimentally, you can compare them to transport model simulation and try to say something about the density dependence of the symmetry energy. So this was a simulation with the simulation done with the BU model in MSU. And so you see here, for example, that you have team 124 on team 112, so different n over z's between projectile and target. And you use two different type of density dependence of the symmetry energies. What you observe is that the degree as a function of time, the system will exchange the n over z. I'm not going now to explain what Ri is. I will tell it a little bit later. But this is somehow telling you that if you have a very strong density dependence, a stiff density dependence, at the end, the two systems will end up with a large difference in n over z after the collision of these two binary system. If you have a more soft density dependence of the symmetry energy, you will have a more faster exchange of neutrons and protons between them, and you reach equilibrium more easily. Now, from an experimental point of view, I would like to show you what has been done at Ganil within our collaborations in these recent years. We have tried the two couple, 4-pi detectors. It's like a ball full of detectors that are used to constrain the impact parameter. Okay, so basically here you measure everything that is produced and you try to understand if the collision is violent or peripheral. Now, since you want to detect after the collision, you want to measure the n over z of this guy that is produced to see how different it is from the initial projectile to study isospin diffusion. We have coupled the forward region with a magnetic spectrometer, which is known to be the best device to measure the n over z of large fragments and also the momentum vector. So we can reconstruct really the dynamics, how much energy was lost during the collision. And we studied these collisions like calcium 40 on calcium 40 and calcium 48 on calcium 48 and tried to see what is the effect of the initial n over z of the system over the final state and the n over z of the guy here. So this is what you can detect with this magnetic spectrometer. So here are all the nuclei that we can produce in one of this collision here. detected by this VAMOS magnetic spectrometer. You can see that there is a large number of nuclei, all of them produced by simply a peripheral reaction of calcium-48 on another nucleus calcium-48, okay? So we can measure them and construct our observables. And what we do is to use the so-called isospin diffusion and the imbalance ratios, okay? Imbalance ratios are defined as I'm going to show you now. So we have studied 4 different reactions where we change the N over Z. So the first one is the symmetric one, because calcium-40 has N equals Z. So this is symmetric nuclear systems. Calcium-48 on calcium-48 is the most neutron-rich system. And then you have the mixture of calcium-40 projectile on calcium-48 target and calcium-48 projectile on calcium-14 target. And you have the collision. At the beginning, you have a certain N over Z of the projectile and the target. You have the collision, and you can have 3 final situations. A situation where the final projectile-like fragment after the collision remains almost at the same N over Z as the initial one, and this is what we call isospin transparency. At the other extreme, we have a situation where the 2 systems exchange completely their N over Z, and we end up with 2 systems that have the same N over Z, and this is what we call isospin equilibration or redistribution, uniform distribution. And between them, we have a sort of isospin translucency, which is between stopping and transparency. So you have a partial change of the N over Z of the projectile and target. Okay? So in order to quantify this experimentally, we choose an observable that we can measure very well with our experimental setup, and which is related, it's not equal, but related to the N over Z of the system here. I'm not saying equal because, as you know, this system is also excited during the collision, so it may lose particles. So what we detect is actually a remainder, a residue of this guy that has been detected, that has been produced in the initial state. However, we believe that this is a good measure already of the N over Z of this guy. It's not perfect, but okay, so this equal is actually roughly equal, okay? But we want to measure the N over Z of this guy. As I said before, with a magnetic spectrometer, you can do this very well. And you construct this quantity. Now, just avoid the details, but it's very simple if you do the algebra here. If you measure this quantity in the neutron-rich collision here, this quantity in the proton-rich collision, and in the mixed region, which is this X here, and you calculate from here, you will observe that this ratio here is equal to 1 when you have transparency, when the 2 guys do not exchange, almost, they don't do anything. You would have R equals 0 when you have equilibration, so complete stopping and redistribution, total redistribution of the neutrons and protons. And if you have something between 0 and 1, then you are in the situation of isospin translucency. It's very easy to deduce this from this formula, so don't go into the detail. This is the important thing to remember. So for example, in this experiment that I was showing before, I show again the picture here. Okay, oops. Okay, we are measuring this guy and try to see how different it is from this guy here, okay, using these R values. Okay, we can measure the N over Z very well. And this is what you would observe. This R value as a function of the impact parameter. Okay, this is not exactly the impact parameter, it's the centrality of the collision. Okay, so don't go into the detail, but this is peripheral collisions, this is central collisions. What you observe in the data, that are these data points here, in peripheral collisions, this R value is very large. So there has been a very small exchange of neutrons and protons between the projectile and target. So it's not 1, because it's not full transparency, but you exchange something. When you go to smaller and smaller impact parameter, there is more overlap between projectile and target. The interaction time is longer because the nuclei stop a little bit. They have more time to exchange neutrons and protons, and these values go towards a sort of equilibrium condition that would be 0 at the end. They don't go to 0 because the reaction does not last enough to go to 0. So these phenomena here, this observation, show that actually we are measuring this isospin diffusion. we take a model, simulate the same reaction using a specific choice of the density dependence of the symmetry energy and try to reproduce the experimental data. And this is done with, in this case, with this anti-symmetrized molecular dynamics model, where you put two different, they are called soft and stiff, two different density dependence of the symmetry energy. And you see that, you try to see which one is closer to the experimental data. So as you can see, we are not there yet. There is some indication in some sense that there is a better agreement with the sort of stiff, this black line here, but we are not there yet, okay? Just to stress that in this field, there is a need for a lot of work and stimulating. It's very nice. So if you are interested, I would invite you to contact people that work in transport models, especially those that like, that are theory. So they might be interested in working in the improvement of these models. For example, putting the production of clusters, as I was sharing before, this is one of the main issues today, and try to find an agreement with the experimental observables. Now, I want to show something that is very popular here in Florence. It's actually students from Florence know, of course. So at some point, people started to complain and say, well, doing experiments with magnetic spectrometers is very difficult. The main difficulties is that you can detect only one fragment per event. The magnetic spectrometer does not allow you to observe events where this projectile after the reaction will pick up into particles. This is lost, completely lost. So also, there's another problem is that you have to have a lot of beam time, because in order to measure all the energy and N over Z distributions in your data, you have to fix the magnetic field inside this detector at several values. So this is what is called this B-row values scanning. So basically, you have to take 2 days of beam time for a certain B-row, then 2 days to. At the end, you end up with 20 days of beam time. And of course, any director in the world would be very, very unhappy to do an experiment like this. Like 1 month of beam time is too much. So people started to think about more modern and more efficient way of doing these experiments. And recently, we have replaced the magnetic spectrometer with a device called the FASIA, which is constituted by many different detectors. It's like many eyes of silicon and cesium iodide. This way, that have properties that can measure the N over Z of these fragments very well. But now, if you have the breakup of the system into many particles, all of them are detected. So you are not losing events, and you don't need this B-row scanning. So in 1 week, actually in 3 days, 2 days of beam time, you can do what you can measure with a magnetic spectrometer in 1 month. So it's a very efficient detector. And the electronics of this detector and also the silicon detectors have been developed here in Florence at the division of INFN. So I don't go into the details, but you know that when a particle enters a material to be detected, it generates a signal that is translated actually into an electric signal. What almost all detectors in the world do is they measure the amplitude of this signal, and from the amplitude they deduce the energy, and then they try to correlate this information with other information to understand what particle it was. Usually this technique allows you to identify particles with a certain resolution, but it's not a great resolution. In the case of this detector, what is done is that the signal is digitized. So you can actually measure the details of the shape of the signal, not only the amplitude. So the raise time, the fall time, and many other things that you can correlate and do a sort of, today there is this machine learning language. It's not the same, but it's like image recognition system where each shape corresponds to a specific particle. So you have a very efficient way to identify particles, even almost online during the experiment, or not so far from the experiment in time. And at the same time, you have an incredibly high isotopic resolution. So you can obtain some features that allow you to use this detector as if it was a magnetic spectrometer and have a lot of nuclei detected event by event. Okay. Okay, this is an example. So first campaign of the intraphasia experiments at Ganil, 2018. We were studying again collisions where we changed the N over Z of projectile and target at different beam energy, 32 and 52 MeV per nucleon. And we wanted to look again at these isospin diffusions by detection of the quasi-projectile after the interaction. And this is an example of what you can do with phasia, with this detector. It looks like a magnetic spectrometer. So nickel 58 on nickel 58, 32 MeV per nucleon. These are all the guys that you can detect. You can see that for each isotope, for each element, you have a lot of isotopes that can be identified, okay? With multi-particle detection capability. So as I said, if this guy breaks up into many particles, you detect them. They are not lost, okay? Then you look at your events. This is another way to establish if your collision is peripheral. For example, if you, for each Z, you represent the longitudinal velocity along the beam axis, you would observe that there are two bumps, but there is a bump that is close to projectile velocity. This is clearly a peripheral collision. Okay, a way to say this is coming from a peripheral collisions. So you can experimentally see these particles that are produced here. They move at a velocity that is not far from the beam velocity. You detect them, you identify them. And then this is an example of determination of impact parameter. So here you use, for example, another observable is the ratio between the momentum in the longitudinal direction of this guy here that we measure and the beam momentum. You construct this parameter. You expect that if you are in a central collision, you have stopping. So this guy that goes in the forward direction will have reduced the momentum. But if you have in a peripheral collision, you have not much loss of energy between projectile and target. So you would observe something that is faster, so with a larger momentum. And this has been used to try to deduce the impact parameter. For example, here in this plot, you have the more peripheral events that are here and the more central events that are here. And then you use a model to try to compare the data to your experiment, to use the model to compare to the data to make sure that your prediction about impact parameter is correct. And then you try to convert this into information about isospin diffusion. And yeah, sure. Yeah. Mm-hmm. So why different limitation? You mean why it has this? Okay, so this is what you observe experimentally, where you see colors. So this is a kind of proton-rich. These are not, yeah, these are not, yeah, not produced. Yeah, yeah. This is basically the same plot like the one that you can have from, usually you use these plots to show a laboratory what beam can produce, right? And you see that here you are in the proton-rich region because you are making a collision of nickel 58 on nickel 58. So it's more proton-rich systems. And we don't see them. Maybe they are produced, but the detector is not capable of seeing them. But if you do this type of plot with a delta E technique, like without digitization, you would see a very thin line here, and probably you would stop at Z equals 6 or 7. So the special feature of this type of techniques is that you can reach up to Z equal 25, and you have like 6, 7, 8 isotopes for each Z. So it's a very special thing that you can have with it. And you can do even better. And this is actually under study now. So now, as I said before, you want to measure the N over Z of this guy. And here as a function of impact parameter, so this is if I show you here, large P red values corresponds to large impact parameter, okay? So if you are in peripheral collisions for different reactions, you can measure the average N over Z of this guy after the collision. And you see that you have different distributions at 32 MeV per nucleon, at 52 MeV per nucleon. You do these measurements and you use this N over Z of this guy as an X variable to construct your isospin imbalance ratio that I was showing before, okay? The one that is equal to 1 when you have transparency, the one that is equal to 0 when you have stopping, and the one in between when you have a translucency of isospin. Okay, so this is the N over Z of the emitter measured, thanks to the fact that you are detecting it directly with your experimental setup. And again, as I was showing before, you have transparency for R equal 1 or -1, R equal 0, you have equilibration. In between them, you have a partial dissipation, and that depend on time scale and symmetry energy. And this is what you would observe in the case of this Indra-Fuzzy experiments. When you go from peripheral collisions to central collisions, if you look at the lower beam energy, the black points here, you see that you go towards more and more equilibrium. If you look at the higher beam energies, the isospin difference is even more because you have less mixing. At higher energies, you have less time in the reaction because it's faster. So you have less time to share and Z between projectile and target. So you cannot reach the same degree of equilibration that you can reach with the lower beam energies. So these are very recent data that have been published and that we hope to compare again to simulations of transport models. And there is a huge activity in transport models to try to be able to reproduce this data and say something about the equation of state and the symmetry energy in the reaction. So again, once more, it's very important to take part in this international effort that exists already to try to resolve and try to make all these models that are different from one another, capable of reproducing the same observables and draw the same conclusion about the input parameters that are used. Then, just at the end, because I think I'm close to the end, yeah. So I just want to measure that there is another observable that is now understudied and that we hope to address in the future, especially in the new laboratories where radioactive beams at these energies are available, which is the emission of pre-equilibrium neutrons and protons, and also of light particles here. This observable has been studied because it is also sensitive to the symmetry energy, but these are very difficult experiments because detecting it is terrible. It's very difficult. So this is a setup that has been used at MSU, for example, where you have this beam that comes here, you have the collision, and you try to detect protons and neutrons emitted from the early stage of the collision. And you try to measure the ratio of neutron and proton yields in different reactions with different N over Z of the colliding system. And then you try to make this double ratio as a function of the kinetic energies of neutrons and protons, okay? So this observable is, you see the very large error bars because it's very difficult to detect neutrons. And this has been compared to the symmetry energy. And this has been shown, for example, that if you use a quantum molecular dynamics model and you change this parameter here is an indication, it gives you a little bit different density dependence of the symmetry energy. And you see that this double ratio that you measure experimentally depends according to models to the density dependence of the symmetry energy, and you try to see what is the density dependence of the symmetry energy that gets closer to the experimental data. And you see that we are not still there. This was published a long time ago, so there is still a lot of work to try to improve the measurements and reduce the error bars, and at the same time try to understand how models can get closer to the experimental data. Okay, so this is basically this parameter gamma here is just the exponent of this dependence on the density of the potential part of the symmetry energy. This is what I was saying before. The closest one is the gamma equal to 0.7 according to this paper here. And of course, I want to mention that as far as neutrons and protons are detected, the laboratory that now has the best potential to investigate on this observable is probably FRIB at Michigan State University. You can have beams with very large N over Z asymmetries. So until now, I've talked about stable beams like nickel 58, nickel 64. There you can have nickel 54, nickel 70. So you can go much larger in N over Z. And the quality of these beams is basically identical to the primary, to the stable beams that we have been using with high intensity, or TIM 132, not TIM 124, but TIM 132, so very neutron rich, or TIM 104, so very proton rich nucleus. Okay, very close to symmetry, actually, to TIM 100. So you can increase the N over Z so that you can improve the measurability of the effects of the symmetry energy, because these effects should be amplified. And of course, since the energies are of this order here, you can go in the higher density region. You can do all such experiments at lower energies with the same beams at FRIB. But I don't have time to go into this in this game. But the least explored region in the symmetry density of the symmetry energy is the suprasaturation density region. And it will be very important to do experiments where you have several observables measured in the same experiment and do Bayesian analysis of these multiple probes to try to constrain better the density dependence of the symmetry energy. And as I was mentioning before, at the moment is the only laboratory where you can detect, and you can do experiments with detectors that have large dynamic range. That means having isotopic resolution from Z equal 0 neutrons up to Z equal 20. And there are also a lot of TPC to extend these isospin effects even to pions and detect pi plus, pi minus. So there is a lot of work and a lot of good opportunities. I don't have time to go into that. As I said at the beginning of my talk, you can use nuclear structure studies by looking at resonance decays and invariant mass spectroscopy. If you are interested, there is a workshop that is organized every year on this topic, where the community in heavy ion high and low energy meet together and discuss techniques to analyze the data, because it's similar problems at LHC and also at low energies. Reconstruct clusters, reconstruct unbound states. There is a very nice study at this moment, even in the ALICE collaboration at LHC, to study the structure of lithium-4. It's a very, very exotic nucleus, like 3 protons and 1 neutron. And we see them at low energies, and we see them at HC, at RIC, with completely different conclusions about the structure. So, you know, this in medium, is there an effect of the medium, of the dynamics in how we see the knowledge of this nuclear structure effects, okay? And since it's late, I go directly, how to do this? I want to go directly here. Oh, sorry. Okay. This is an example, still using fuzzy. So in the nuclear physics domain, if you correlate in the final state all 2, 3, 4 particles that you see in coincidence, and you construct the invariant mass of the total energy in the center of mass of the 2, 3, 4 body system, you will see a lot of structures of a lot of states that you can produce all in the same collision. So you do one experiment to study the equation of state, and in the same experiment, hundreds of states, like carbon 11 into alpha and beryllium 7, carbon 12 into 3 alpha. You can, it's, for example, by looking at multiple alpha correlations. And you have all of this in just one single experiment. So we hope that in the future facilities where you can have deep beams and push more towards the proton-rich line, or push more toward, the proton drip line, or push more in the neutron-rich side, we can increase the amount of nuclear experiment and link the structure properties that we observe to the bulk properties of the equation of state. And then I want to conclude. So basically, my message is that heavy ion collisions are a tool to study the symmetry energy and nuclear transport under laboratory controlled conditions, in the sense that you can somehow control the density and the temperature with the beam energy, and also with the choice of the mass of the projectile and target. The impact parameter you cannot control, but you can classify the final event that you have collected into different impact parameters. So you have an end on that. And of course, this physics is important for astrophysics, as you can see. I didn't talk about the neutrino sphere of the supernova, which is another topic very important in this field. And then I showed something about isospin fractionation, isospin diffusion and drift, and other probes that are expected to provide strong probes. And of course, we need complete and reliable measurements on the one hand in the future, so experiments that can measure these observables all together and not doing experiments only for one or the other. But at the same time, also a lot of efforts in improvements and analysis of transport models. This is already ongoing, but lots of human power is required in order to improve that. And then I showed you also that there is a lot of work that you can do in the same events, even to improve models, so looking at this invariant mass spectroscopy and femtoscopy to link together nuclear structure and dynamics. And I just pointed something about the possibilities offered by exotic beams in the future, both for experiments and for theoretical physics. And I think multi-purpose projects that are typical of heavy ion collisions are nice because they allow to do a lot of physics at the same time and understand better, constrain better the quantities that we want to study. Okay. And of course, you are welcome to participate and join these crazy challenges. And it's crazy, yeah. Yeah, so Giuseppe, I have a question about we're looking at some observables and I was wondering that for instance, also whether whatever behavior of the symmetry, they also have an impact on where you are looking for something that will tell you about the symmetry. So is it clear that it's a single correlation pattern or it's a more complex? It's more complex because the reason why we do experiments by changing the n over z and keeping all the other things intact, like impact parameter. You look at the same impact parameter, same beam energy, possibly same mass, but change the n over z. And then you look at all, have you seen that all of these observables are ratios between something that happens in the neutron-rich system and something that happens in the symmetric systems, most of them. The reason to do that is to try to amplify, to see better the effects of the symmetry energy that of course will mix also with the effects of the symmetric part of the equation. Other effects I did not talk about, for example, the momentum dependence that generates these effective masses of neutrons and protons that are modified. This also plays a game into this thing that complicate things. So it is important to do experiments where you look at relative observables from one reaction to the other to try to have, what is the effects of the n over z over the symmetric part. And on the other hand, I think what I was mentioning here, multi-purpose project, more observables measured in the same experiment. So for example, in the same experiment, measure those observables that are sensitive to the symmetric part together with those observables that are sensitive to the asymmetric part, all together. Flow, correlations, isospin, fusion and drift, without changing experimental setup, without doing experiments in one laboratory or another, which is experimentally means that you are changing completely everything. So there is, this is when I talk about effort, experimentally to improve measurements. I think that we know how to do experiments very well. I think we still don't know how to measure several observables in the same experiment. For example, measure neutrons, detect neutrons together with these guys coming from isospin diffusion and drift. This, this would improve the amount of observables that are sensitive to the symmetry energy and improve the constraints and single out, this, I think it's not a one-to-one correspondence. That's why we need to do better experiments.
And also enforce so I want to ask, does this two experiment lead to different results?
Yeah, sure.
Why is this different? Because time reversal is broken?
Oh, no.
Yeah.
It's two different, the same experiment. For a week, you do calcium 48 beam on calcium 40 target, and you collect the data.
Yeah.
And then the week after, you change the beam and the target. You produce a target of calcium 48, and you accelerate the calcium 40.
What's the need of
Oh,
yeah,
the projectile. So I can show you all of the. Yeah. But so if you see all of these experiments, the part that can measure the n over z very well is always in the forward direction, because you need to have a particle that has enough energy to break, to break the wall, in the sense that it has enough energy to penetrate deeply inside the detection material. If you have a particle, of course, in the other way around, of course, you will have something in the target happening, but they move so slowly that they are stopped in the first layer of your detectors, and you only see an electron signal, and you can say anything about the identity of the particle. So if you want to improve the identity, the measurement of the identity, you need to have a large kinetic energy. So that's why you exchange this.
In this experiment, you could have information about the density dependence of symmetry energy up, let's say, twice.
Yeah, maybe even less. This energy is actually even less. Usually 1.1 usually. Yeah, I would say. Yeah. If you want to go to twice, that's FRIB, what I was mentioning. So if we do experiments at FRIB energies, oops. Yes. So that's why. Oops. Here. Oops. So basically, this region between 100 and 300 per nucleon is a region where you can explore the up to 2.5. And indeed, the transport models, if you plot the density as a function of time, you see that the system spends quite a lot of time, like 50 Fermis over C, around 2.5 saturation density.
You show figure with the density dependence of symmetry energy, showing symmetry energy that
Yeah, we know that. Don't like it.
No, because microscopic calculation interaction.
Yeah, of course. Yeah. Yeah, of course. Yeah. Right.
90%. That was the increasing energy, but also some of the scan interaction.
Yes.
Then was fixed also for phenomenological interaction. This is the reason the scan beyond was created.
That figure.
The
Bayesian
analysis, then those scan interactions
are removed. Yeah.
Because
they are not used anymore. Yeah, this figure comes from a very old paper by Brown in 1999. So it's 25 years. Long time ago. Yeah, yeah.
The question, so let's take GIUSEPPE